This is a Mode 3 experiment, heat transfer in coffee experiment by Muhammad Azhar Aditama, name 1318225, and my lecture guardian is Pak Firman. There is three objectives in this experiment. Firstly, to determine the optimum drinking period of hot coffee on a variation of cups and explain their effects. Secondly, to determine the effects of using a variation of material on the heat transfer and the effects of a variation of exposed surface area on the convection coefficient. And lastly, to determine the effects of blowing wind speed on the temperature and heat transfer. This is the equipment used. So there is Arduino connected to a computer for data collection. There is two thermocouple and an ambient temperature sensor attached. There is a weight balance to measure the weights of the cups. There is three different cups with different sizes and material. There is an electric kettle to serve the temperature at to serve the coffee at high temperature. There is an anemometer to measure the wind speed and insulation for many purposes. This is what the Excel data collection will look like. There is a time interval of 30 seconds for each data. There is three temperature measurements. The first one is temperature of the coffee. Next is the temperature of the cup, and lastly the room temperature. This is the basic theory. The major theory is the Newton law of cooling, which is the heat flux equals to the convection coefficient times the temperature difference. Another major aspect is the thermal energy equation, which is Q equals mc times delta T. The assumptions made to get this equation is firstly incompressible liquid with negligible kinetic energy and potential energy changes and negligible work. Secondly is this negligible viscous dissipation, as shown as in this figure. This is the standard condition of a coffee with no lid. So basically there is three heat transfer occurring. Convection through the walls of the cup. There is convection from the coffee to the air, radiation from the coffee to the air, and conduction from the coffee through the walls of the cup material. Now for this experiment, radiation is can be neglected as it doesn't significantly affect the heat transfer. The first objective. Now the reason why we are finding the optimum drinking period is because a lot of coffee drinkers, they want to drink at hot temperatures, right? But however, at usually at serving temperature of 75 degrees, at this serving temperature, it can cause a scald that damages the skin. And hence, from the paper conducted by PubMed.gov, it shows the temperature range that is safe and satisfies the drinkers, which is at 60 plus minus 8.3 degrees Celsius. As a result, I will construct a temperature profile for this range of temperature. This is the procedure. We have the Arduino connected to computer and a thermocouple attached to the walls of the cup and a thermocouple inside the cup. So next, I will weigh the ceramic cup using a weight balance. I will brew the coffee and I will pour it to the cup, and afterwards I will measure the weight again. And whilst the experiment is ongoing, I will stir the brew constantly to distribute the heat evenly. And based on the Excel, we can plot the temperature time graph, and we can analyze from the temperature distribution graph. Now this is the data collection of the analysis. For the first four data shown from this graph table, it is the temperature without the hot coffee being served. And the reason for this is because initially, when without the coffee on the cup, the temperature of the thermocouple is different in comparison to the ambient temperature sensor. Therefore, for all of this experiment, the room temperature is based on the first four data of the experiment. And furthermore, the data taken is until 75 minutes or 4,500 seconds, which is where the steady state condition is close by. This is the temperature distribution of a ceramic cup. This is the, as you can see from the figure, there is the heat transfer of fluid obtained from the data, which is this, and the heat transfer of the cup, which is this. And as shown on the figure, the optimum drinking period is after serving is 9 minutes until 27 minutes. Now we have two variations of cups. The first one is the a smaller size ceramic cup with a smaller exposed surface area. Next variation is the different material, which is insulated stainless steel that has a vacuum in between the walls. The stainless steel itself has also a smaller specific heat capacity in comparison to ceramic. This is the temperature distribution of smaller ceramic cup. This is the temperature distribution of the stainless steel cup. Now this is the analysis and conclusion. So the data above is taken after the hot coffee is poured and without the lid, and as you can see, it shows the exponential graph with their respective equations. From the material aspect, from the exponential equation of the fluid, we can see that for the insulated stainless steel, it has the lowest exponent value in comparison to the ceramic cups. And this is because the stainless steel itself, it has a double wall design, which is out of vacuum, which creates a pocket of air that doesn't allow heat to dissipate as quickly. And therefore, as you can see from the graph, there is a smaller rate of temperature change, and the heat transfer that was obtained of the cup, it is way smaller than the ceramic cups. The small heat loss or heat transfer can also be shown from the optimum drinking period. As you can see, the optimum drinking period where the cup maintains a temperature of 60 plus minus 8.3 degrees is 35.5 minutes, which is way longer than the ceramic cups, which shows that the heat loss is significantly small in comparison to ceramic cups. Another reason why the heat loss is small for stainless steel cup is because the stainless steel itself, the specific heat capacity, is smaller than the specific heat of ceramic material. Next is the exposed surface area and size aspect. So from the exponential equation of the smaller ceramic cup and the normal size ceramic cup, we can see that for the smaller ceramic cup, it has a smaller base value, which means that the ceramic, it is less deeper than the ceramic cup, as you can see from the graph itself as well, meaning that the smaller ceramic cup, we know that the smaller ceramic cup has a smaller area, exposed area, right, for 4.70 centimeters squared for the smaller one and 47 for the normal size one. You can see that this effect has has made the smaller ceramic cup to have a smaller rate of temperature change, and therefore it has caused the heat transfer, the heat loss for the smaller ceramic cup to be less in comparison to the normal size ceramic cup, as you can see from the values here. As a result, we can conclude that because due to the fact that coffee cools by heat being lost to the surrounding, the heat loss will be larger when the exposed surface area is larger, as the fluid coffee particles will interact with the surrounding more, and therefore the heat transfer by convection is higher from the fluid to the air. Next objective is to determine the effects of material and exposed surface area. This is the basic theory. For the exposed surface area, it is essentially the Newton law of cooling. As we can see from this equation alone, that if we increase the area, the convection coefficient will decrease with the same temperature difference NQ. This is what the experiment of exposed surface area will look like. So everything will be covered of the cup except the upper part, the exposed area with the air. So from this diagram alone, we will only have convection that is related to the thermal energy only, and conduction will be neglected. For the material aspects, we want to associate the thermal energy of the fluid with only conduction. Therefore, we need to neglect the convection, and this can be done by insulating every walls of the cup, all around the cup essentially. Therefore, we will neglect the convection by mass transport, which is from the coffee to the air, and we'll also neglect the convection that occurs at the boundary between the cup and the air, or in other words, the convection that occurs through the walls of the cup. Since we are for the material, since we are covering all over the cup, there is only one way the heat can escape, which is through the cup material and through the insulator, which is styrofoam. And therefore, we can obtain the Fourier's law by the assumptions of one-dimensional steady-state conduction in a plane with no heat generation, constant thermal conductivity, and the temperature varies linearly with distance, and we can get the Fourier's law equation. As we are covering everything with insulation, we can only relate the thermal energy equation, which is Q equals mCp delta T, equals to the Fourier's law of conduction. And afterwards, we can get the equation to get the thermal conductivity. As you can see from this, theoretically, if the thermal conductivity increase, the heat transfer will increase. And also, since we are focusing on the heat transfer from the fluid to the insulation material, this will be positive. For the exposed surface area, since we are only relating the convection with the thermal energy equation, we get this relationship, and we can get the H value. This is the procedure of determining the effects of exposed surface area on the convection coefficient. I will arrange the Arduino as usual, and the styrofoam will cover all around the cup except the top of the exposed area where convection will occur. I will brew the hot coffee, and I will obtain the data of temperature with respect to time with an Excel with a time period of 75 minutes as usual, and I will conduct a second experiment with different exposed surface area. This is the temperature distribution graph. This is the exposed surface area. So we have a small size ceramic cup with a more size ceramic cup with the different area. For the area that is larger, we can see the value of H is this, and for the area that is smaller, we can see that the value of H is actually larger than the area of the larger area, and this essentially proves the equation from the theoretical theory. It proves that if the larger the area, the smaller the smaller convection coefficient will be, as you can see from this. However, from this experiment, since we need to fill the whole cup, the mass will be different. This is the procedure of determining the effects of material of cup on the heat transfer. So we need to arrange the Arduino and the software as usual. The cup will be fully insulated using styrofoam, hence only heat transfer from fluid is to go across the cup and insulation material, as you can see from here. I will brew the hot coffee, and I will close the cup with a lid, as you can see, and also I will cover it with the styrofoam on the top, just for further insulation. And now I will obtain the data of temperature with respect to time for a time period of 75 minutes, and I will conduct a second experiment with different material, which is stainless steel, that has the same thickness and size as the ceramic cup. This is the data, and this is the temperature distribution. As shown in the figure, the styrofoam is a very good thermal insulator because the rate of temperature change for with the styrofoam insulation, it is very small in comparison to the temperature rate, the rate of temperature change of ceramic cup without the insulation. And based on the data, we can get the thermal conductivity. For the ceramic cup, we get this value of thermal conductivity 0.06. Next is for the stainless steel. For the stainless steel, we get the value of thermal conductivity that is lower than the ceramic cup. Furthermore, from this temperature distribution, the temperature of stainless steel cup when insulated is way larger, or the rate is way faster than the one without the insulation styrofoam. And this is because we can see from this picture that around this insulation styrofoam, there are gaps in between the walls of the cup as well as the insulation material, and therefore when the heat is lost through the cup of material and is trapped inside the insulation material, it will increase the temperature of the cup or the temperature of the thermocouple that is attached to the walls of the cup, because the heat are trapped inside these gaps of walls. This is the conclusion of the experiment. So from the figures, we can see that the covering the ceramic cup with styrofoam, the temperature of the cup has increased drastically, as you can see. Especially with the ceramic cup, it increases very drastically in comparison to stainless steel. And this is because the ceramic have a higher thermal conductivity or lower thermal resistivity, so heat loss from the fluid through the cup of material and to the insulation is way higher. It can pass through easily. And since I explained before, since one thermocouple is attached to the outside of the walls of the cup through the gaps, and heat is essentially trapped within those insulation gaps, the temperature will increase drastically with the ceramic. However, for stainless steel cup, since it has a double wall design, as I mentioned from before, there will be less heat trapped in the insulation gap because there is less heat loss. Also, furthermore, from the first objective experiment, we also know that the stainless steel has a lower specific heat capacity than ceramic, and therefore the heat loss will also be less. This is the suggestions or saran of the experiment. To determine the effects of exposed surface area experiment, what I did was I used a smaller exposed area ceramic cup. It also has a smaller size than the normal ceramic cup, and this can affect the heat transfer. And hence, for the suggestion for this experiment, the size of the smaller exposed surface area of the ceramic cup needs to have the same size as the normal size ceramic cup. And also, since the cup needs to be filled up to fully until the top for the exposed surface area experiment, and since the sizes are different, the mass will also be different in the thermal energy equation, Q equals mc delta T, and therefore it will affect the heat transfer. The last objective is to determine the effects of blowing wind speed on the temperature and heat transfer, and we can relate this to the boundary layer as well. So for the basic theory, we have two types of boundary layer, the velocity boundary layer and the thermal boundary layer. Both of these boundary layer is formed by a fluid flowing over the surface. The shape of the velocity boundary layer is caused by the shear stress from the surface, which reduces the fluid velocity. And increasing the distance from the surface, the velocity increases until it reaches a free stream velocity. For the shape of the thermal boundary layer, it is caused by the temperature difference of the fluid free stream and the surface temperature. And increasing the distance from the surface, the boundary layer will be larger as the heat penetrates more into the free stream fluid. Furthermore, as the distance increases, the magnitude of the temperature gradient decreases, and therefore the heat loss of the surface and the convection coefficient decreases. The thermal boundary layer is also associated with the Newton law of cooling. This is the derivation of the hydrodynamic solution at first convection, and we get this equation. And this equation is used to see the effects of the wind speed on the hydrodynamic layer. As we can see, theoretically, as the wind speed increases, or the U infinite, the boundary layer thickness decreases, as the larger free stream velocity will cause a thinner boundary layer. This is the derivation of the heat transfer solution as first convection. So from this equation, you can see that as the temperature gradient increases, the convection coefficient increases. Also, as the wind speed increases, or the U infinite, it will cause if this increases, it will cause an increase in heat loss and convection coefficient. This is the procedure of the experiment. So I will set up the Arduino as usual. Then I will apply a high wind speed from a fan or a forced convection constantly on a brew for 75 minutes. And I will measure the temperature with respect to time at interval of 30 seconds with thermocouple. And I will measure the wind speed using an anemometer. And I will plot the temperature versus time graph. And I will compare the results obtained with that of no wind speed applied, that was obtained from the first objective experiment. So this is the temperature distribution of the ceramic cup with wind flow of 3 meter per second, and the temperature distribution of ceramic cup without any wind speed applied. So using the same ceramic cup with the same mass, you can see that from the temperature of the coffee, or the blue line, you can see that from the equation the exponent value 0.011 is higher than the one without the wind flow applied, the 0.08. Or we can say that the temperature distribution is way steeper for the ceramic cup with wind flow applied, and this is because the wind cools down the coffee, and the heat loss is therefore larger, and hence the rate of temperature range is faster. With the wind flow at 3 meter per second, it will reach steady state condition faster as it cools down by the fan. Also, as shown in the figures for the temperature of the cup, the base value when the wind flow 3 meter per second is applied, it is significantly lower than that of the wind speed, as you can see from here. It is way smaller, and therefore it shows that the cooling effect from the wind flow drastically suppresses the heat transferred to the cup material from the fluid. Furthermore, the wind speed caused by the first convection will decrease the temperature because the convection coefficient and the heat loss across the cup is increased. And therefore, it can be concluded that as the wind speed increases, the convection coefficient will increase. As you can see from the, if we relate the temperature distribution and the rate of temperature change with the Newton law of cooling, we can see that as the wind speed increases, the convection coefficient will increase, and therefore the heat transfer rate is higher. As we know, there will be convection occurring from the coffee to the surrounding air and the walls of the cup to the surrounding air. Therefore, we can relate this to the Newton law of cooling. You can see from the velocity boundary layer, from the temperature distribution graph of the ceramic cup with the wind speed applied, as shown previously, it proved that as the wind speed increases, the boundary layer thickness decreases as the larger free stream velocity causes a thinner boundary layer, shown in this equation, and therefore the convection coefficient is smaller. Furthermore, for the thermal boundary layer, that was as shown in the temperature distribution graph of the ceramic cup with wind speed of 3 meters per second. As the wind speed is increases, or we can compare the wind speed of 3 meters per second in comparison of no wind speed, it causes an increase in heat loss and convection coefficient, which relates to this equation. So as the wind speed increases, the heat convection coefficient increases. This is my RAB. Total will be 394 K. And this is the suggestions or saran of the whole experiment. As we know, for the standard room temperature, the temperature of the thermocouple is different than the ambient room temperature sensor, which is explained in the first objective experiment. And therefore, the thermocouple is not very accurate equipment to measure temperature, which affects the overall results. For every experiment, it is only conducted once due to the fact that there is a lot of experiment with variation of materials and sizes, and therefore, and for the fact that I'm using an electric kettle to heat, I only conduct it once because it will, if I do it more than once, it will cause a high electricity bill. If more results of the same experiments are obtained, the experiment will be more accurate and errors can be outlined.